Hey everyone, we're going to be covering metabolic recovery in this particular lecture, and we'll talk about things like muscular recovery, etc. in future lectures. But if you consider for a moment after you've exercised yourself, say you've gotten really out of breath, heart rate is elevated, etc., what that's a clear illustration of is the metabolic components of recovery when we're talking about exercise. So again, within that 3-5 minutes or whatever after exercise, when you're again still very alert, heart rate's up, breathing is heavy, and what that is primarily is this component where your phosphocreatine system, amongst other systems, are getting replenished through aerobic respiration. So there's a really good chart that's going to come up in a couple of slides that will help illustrate this. So, but for now, if you can just picture, again, going back to your anaerobic systems, so phosphocreatine, ATP, PC systems, purely really depleted. You've just had let's say a fitness class or something. You're really tired. So that continued respiration is trying to use your Krebs and ETC to generate the ATP needed to replenish that 10-second worth of energy with the ATP PC system. Okay, so that's one of the things that happen. The other is this slow clearing out of your system of the extra hydrogen protons that end up getting accumulated during exercise. So recall different mediators that usually soak those up or our blood system that helps buffer it, and so it just allows us to return to zero or get back to a good pH balance for our cells to operate again and produce ATP at a good rate. Okay, so when we consider post-exercise oxygen consumption, what happens during that period of time, so you finished exercise, you're still breathing heavily, is essentially the measure or the amount of oxygen that we take in after exercise above what our normal resting values would be. When we're talking about a term called steady state, that's essentially all the energy that we need is being met through aerobic metabolism. Okay, that's a really important component of steady state, is it's aerobic metabolism that's meeting our needs. So you can think of this perfect demand of energy through aerobic metabolism, and then the amount of metabolic substrate feeding in to produce that is into our mitochondria is getting perfectly out the amount of ATP we need for that exact workload. Okay, so steady state. And we'll cover that more when we get to the last lab, or your aerobic lab. And something to note there, just so you can picture it in your head, is usually there's a bit of a lag between the output that you put out when you hit a new workload and when our bodies catch up to that workload aerobically. So you'll see it takes about 2 to 3 minutes for our bodies to catch up to this new workload, assuming that we're staying in an aerobic effort level. Okay. Oxygen deficit. So I know the terms seem somewhat similar, oxygen debt and oxygen deficit, but they definitely speak to two different parts of our post-exercise oxygen consumption. And what it speaks to is primarily that component where at the start of exercise, our oxygen use is much lower than our actual energy production. So there's this discrepancy between ideally what we'd be making through aerobic metabolism, but we're not quite there yet. So it's kind of a backwards or deductive way to figure out how much anaerobic energy that we're making during that period of time. Like I mentioned with steady state, it takes about 2 to 3 minutes for our oxygen consumption to match whatever our ATP demands are. Okay, great. So turning back to oxygen debt, and if you recall, that's the part after we're done exercise, once we've stopped. we have two phases in that. One is the first rapid phase, 2 to 3 minutes, where most of our intramuscular phosphocreatine system gets resynthesized or regenerated. And you can think, if you're doing like hard interval work, like strength training, for example, if you do a really hard set where you deplete or use up most of your ATP PC for energy in that first 10 to 30 seconds of whatever lifts you're doing, if you break for about 2 to 3 minutes, you'll be able to fully regenerate that ATP PC system mostly, and be able to go again in theory. So you'll have enough anaerobic energy available for you. Okay. The slow phase is different. So it takes several hours, and again, this kind of depends on who you are, what your training status is, and what the workout was like. But typically, it's when aerobic metabolism regenerates intramuscular stores of ATP, of glycogen, of clearing out resetting blood lactate, clearing all of that out. Okay, and so when we're talking about that phase in particular, 70% of lactate is aerobically metabolized. Okay, so again, if you're thinking back to the Cori cycle and curious about how much that plays in effect, that's really only 20%, and then 10% is through gluconeogenic amino acids and resetting ATP and regenerating intramuscular and blood lactate levels, right? So we want to reset those, accept the lactate as an acceptor for protons, and these are the ways that it's done. Okay, as I mentioned, muscle and blood oxygen stores kind of get back up to rates at which they were, or levels which they were prior to exercise, and things like body temperature and heart rate and breathing all return to normal. And so again, that can take several hours depending on what the workout was. Now, I mentioned this without saying it, but EPOC, or exercise post-oxygen consumption, that occurs again once exercise is done. And that's really the point in time where we're trying to pay back or replenish our systems that we originally would have had or had a backup of from our anaerobic systems. Okay, so again, I think this is much easier to see on this graph here, and then I'll kind of re-explain it a second time for you to really solidify things. So we'll start at the start here. We're at rest. This is how much oxygen we use. This is over the course of time during our workout on this axis. And if we start with our resting oxygen consumption at baseline here, this is what the dotted line is. We can see once we start exercise, or even start thinking about exercise, we notice that our oxygen consumption comes up. Okay, and as we continue to increase our exercise to the point in time and workload where we reach steady state, so that would be this flat line up here, we notice that this whole corner of O2 deficit exists, right? So this is our deficit. This is anaerobic energy right here in this component. So why is that important? Well, at the end of the day, after our workout, when we're done and we hit the end of exercise, okay, what will end up happening is we have to pay back, and then a large dividend, our O2 debt, or EPOC, right? Our exercise post-oxygen consumption, to reset all of our body systems back to nominal, or back to normal, or equilibrium, right? So again, this amount here. So normally if we started exercising and we got all of our ATP through our aerobic system, boom, we'd be right up at that corner and we just stay at steady state. But this lag, or this deficit that occurs because our anaerobic system is trying to help us get up to our steady state with aerobic activity, we have to pay back that debt of that O2 deficit that we generated. Okay, so this is a lot of the times, or EPOC is a lot of the time, what people refer to as afterburn. So after you do a workout, You'll hear in the health and fitness industry this like afterburn effect where you're still burning calories, and that's true to a point here through EPOC. Okay, you're sort of replenishing all your ATP. Okay. Next question that I'm sure you're curious about is, how do you maximize this recovery? Well, in a previous lecture, I mentioned that story where you see hockey players after a hockey game, or like especially in the playoffs, they'll do their interviews and they're all on bikes spinning. And, at first glance, you might be like, wow, like you just played a really hard hockey game. Why are you cycling now on a stationary bike? And the reason for is maximizing the metabolic recovery. Okay, so here's how it works. There's two types of recovery. There's active and passive. Now with active recovery, this is what would happen if you got on a spin bike after a hard workout, is with this light to moderate activity, you decrease blood lactate faster than if you're to do nothing. So yes, you have blood lactate in your blood, and again, generally we think of this as a bad thing, but if you recall now with your new knowledge of the Cori cycle and what we actually use lactate for, it's fine because we use this lactate that we have to in the blood to regenerate, recycle it to be able to be new end receptors for anaerobic activity and glycolysis, but then also to be able to create new energy for our cells. Okay, now the key is it must be quite low, so it needs to be well below your lactate threshold as far as the workload, right? You're not getting on the stationary bike and having another really, really hard workout. So to put that into some actual context with numbers, the idea is if you're cycling, you're about 30 to 45% of your maximal amount of oxygen consumption. So you can think of a 3 or 4 out of 10 effort level, 10 out of 10 being everything you've got. And if you're running 55 to 60%, it's actually quite challenging to get good active recovery while jogging. But again, the end goal is it must be below lactate threshold. Okay, so again, the benefits to that is blood lactate decreasing faster. There's a good slide after this that'll demonstrate that. Passive recovery, also really valuable, but for a different reason. In this case, we get higher levels of muscle glycogen reforming. I mentioned this at the beginning of this lecture. This is one of the things that happens with metabolic recovery. And again, one of the main keys with this is we want glycogens to get replenished, right? Why is it more than if we were doing active recovery? Well, it kind of makes sense that if we're still moving, still being active, our body's still utilizing blood sugar or blood glucose for the activity rather than starting to store it in our muscles as glycogen. Okay. And ultimately the difference between trained and untrained individuals for the time of recovery or types of recovery and at the rate at which it happens is pretty minimal. There's some studies that show those with like higher levels of VO2 max or maximum oxygen consumption can recover a little bit quicker, so they clear out lactate a little quicker, and that's likely through the process that is assisted through aerobic metabolism as far as recharging or replenishing lactate, as we discussed last slide. But typically you need some time for that to occur. Okay, and then as promised, here's a good illustration of the difference between active and passive recovery. If you look at the bottom axes here, we have recovery time in minutes, and on the Y or the vertical, we have plasma lactate. So this is lactate in your blood. If we end exercise here, you notice that a lot of lactate travels to the blood to get regenerated, and part of that in passive recovery stays high quite a lot longer, the first hour post-exercise. But does get down to pretty close to baseline, similar to active recovery. Active recovery, however, you don't see that same peak. Okay. So I guess that's the end for the recovery section as far as metabolic recovery and EPOC, so exercise post-oxygen consumption. Really key terms there and important concepts to understand. Okay, cheers.